Hello. Now that you've gotten a bit of review of solving systems of equations, we're going to get into something called matrices. And matrices, singular matrix, are not just what you saw in the movies, those 3 movies with that same name, The Matrix. You kind of saw them in there, but we're not going to be jumping back and forth between reality and a world that exists in your mental state. We're just going to be using a mathematical version of this to help us with things like solving systems of equations. So what is a matrix? Well, a matrix is a rectangular array of numbers enclosed in brackets. So it might look like something like this. 2, 3, 7, 5, -1, and 10. So that's an example of how a matrix might look. So it's in a rectangular shape. You've got rows and columns. Like you have 2 rows in this case, and you have 3 columns. And a matrix is always, when you talk about the size of a matrix, it's always R by C, rows by columns. So this is a 2 by 3 matrix. I remember that the rows comes first because I think of RC Cola or an RC car. Like that's what they used to call those little radio-controlled cars, RC radio-controlled. But number of rows times by number of columns tell you, to identify like the size of the matrix. And each of those numbers inside is an element of the matrix. Okay. Your matrices can also look something like this, where you have what's called an augmented matrix. And that's actually what we're going to be working with quite a bit in this lesson. So you might have numbers like, just like in the previous matrix, then you might have this little vertical line and some more numbers past that. Okay, that's just an example I've been throwing out there of what an augmented matrix looks like. So this one is 3, it has 3 rows and then 4 columns. So this one's a 3 by 4. Okay. Now our goal is to take a matrix and use it as a tool to help us to solve some problems. So in order to use this tool, we need to know what we're allowed to do. Okay, so what is allowed? Okay, they call these matrix row transformations. We're allowed to interchange any 2 rows. So you can take an entire row and put it in a different position as long as the other row goes into that position. Interchange them, swap them. But when you interchange a row, the entire row has to interchange with the entire other row. You can't just take pieces and move them. Multiply or divide. The elements of any row. By a non-zero real number. So you can take a single row, pick a number, a non-zero, don't want to multiply by 0, that would get you nowhere fast. But you could pick another non-zero real number, like 2. You can multiply the entire row by 2. But if you do it to that row, you got to do it to the entire row, to every element in the row. And then you can always replace any row by the sum of the elements of that row and a multiple of the elements of the other row. Remember, multiple you can always multiply by 1, so you could just take another row and add it. Or you can take a multiple of it. So being able to use these three things will allow us to work with this matrix and transform it into something that looks very different from how it started, but will effectively give us solutions to what we're looking for. Okay, so we're allowed those three rows, or those three things. So why do we want to be able to do this? Well, we're going to look at something called the Gauss-Jordan method. All right, let's say that you're wanting to solve this system of equations. 4x minus 3y equals 14, x minus 2y equals 1. Okay, you'll recognize these as two linear equations. 4x minus 3y equals 14, you can graph that, it's a line. X minus 2y equals 1, you can graph that, it's a line. And where those two lines intersect, you get the solution point, the solution for that system of equations. It's the point that they both share in common that will work in both. Analytically, if you don't want to do it graphically, you can use substitution method or the elimination method. And you've done that quite a bit in the previous lesson. But we're going to put this into matrix form, and then using the rules of the transformation of the matrix, we're going to be able to get the solution that way too. And essentially, doing these transformations, we're following the same kinds of steps as when you use like the elimination method in solving these systems. So hopefully I'll be able to show that to you clearly enough. Okay, so what we're going to do is we're going to start by drawing an augmented matrix using just our coefficients and constants. So the first equation will go in the first row. Coefficient 4, coefficient -3, and we're doing an augmented matrix where the solutions, the constants, are over on the right side there. Okay, and we're just dealing with coefficients because we're making this into a matrix. And just dealing with these numbers, we can be able to work it out much the same way as when you're working it out and dealing with the coefficients, except you won't have your x and y written every time, but at the end you'll know which one's x and which one's y. All right, because you know that your x's go first and your y's go second. So, all right, so the second equation we put in the second row, 1 for the 1x, -2 for the -2y, and then the 1 for that constant that it equals. So do not write your x's and y's in there. Just those coefficients and then what they equal. So, and notice too that you really want your equations to be in that standard form when you start here. You really want your x and y to be in order on the left, and you want your constant to be over there on the right of the equal sign. That way you can get your matrix set up. All right, then we're going to use what we know about transforming these matrices, and in the end we want this matrix to look like this. Okay, So we're going to use these rules of transformations to get it to look like that. We want a diagonal of 1s, and we want everything else to be 0s. We want from the top left to the bottom right to be 1s, and then everything else to be 0s. So essentially, what we'll have is an equation like 1x plus 0y equals A, 0x plus 1y equals B. That's what that matrix stands for. So we'll have our solutions. We'll have x equals A, y equals B. So whatever those numbers are over there on that right-hand column, that far right column, that'll be our solutions to our system. Okay, so let's do this. Let's use the equations I just had there. I'll rewrite them for us. And let's use some techniques to get that augmented matrix to where we want it, into that diagonal form. We want to reduce it down to that diagonal form. Okay, so we have, let me rewrite my matrix. I like to draw little arrows to remind myself that this next one's the next matrix. All right. It's a good idea to start with getting a 1 and like start getting that diagonal of 1s going. We want to get the upper right or upper left, excuse me, upper left 1 in place. We want to do that first. So we want to try to get our 1 in place here. Then we want to work on our 0s underneath, and then kind of curve our way around and get our, we need a 1 in place over here, and then we're going to need a 0 over here too. So what I'm going to do is I'm going to go ahead and swap rows. I'm allowed to do that. I'm allowed to interchange any 2 rows. So I'm going to put the top row on the bottom, and I'm going to put the bottom row on the top. I'm allowed to do that. If you were writing these still with x's and y's, it would just be writing x minus 2y equals 1 on top and 4x minus 3y equals 14 on the bottom. Okay, it's perfectly legal. All right. My next goal is to try to get a 0 underneath that 1. So since I'm allowed to basically add 2 rows or multiples of rows, I'm going to use that to help me get that 0 that I need. So I'm looking at this and I see, in the upper row, in the first row, I have a 1 there in that corner. And then I need to think about what multiple can I make of that and add it to that second row so I can get a 0 where I need it. Well, I can use -4. If I multiply this first row by -4, then I can add that to the second row. If I multiply that first row by -4, I'll have -4, 8, -4. Okay, so the first row is going to stay the same. I'm not actually changing it. I'm going to leave it in the matrix the same way. But I'm going to use this multiple of the first row and add it to the second row. So -4 plus 4 is 0. 8 plus -3 is 5. -4 plus 14 is 10. And already I'm getting very close. If I wanted to stop here, I would know that x minus 2y equals 1, 5y equals 10. So it's like you're working your way, it's like you eliminated your x, and then now you can solve for y, like if you were doing it the other way, if you're using your elimination method. But we're not doing that, we're doing matrices. So we're going to, for now, the first row is going to stay the same. And we're going to concentrate on getting a 1 right here. Finish that diagonal. So how are we going to do that? Well, we're going to divide this row by 5. Same thing as multiplying by 1/5. You're allowed to do that. You're allowed to multiply or divide the elements of any row by a non-zero real number. Multiply or divide. So 0 divided by 5 is 0. 5 divided by 5 is 1. 10 divided by 5 is 2. Almost there. We now know from that bottom one that y equals 2. And now if we get that 0 right here to complete what we're doing, then we will have it solved. Okay, so it looks like I didn't think about my space well enough, so I'm going to be squishing some stuff in right here, sorry. So I want to go ahead and get that last matrix written in the same slide. All right, so what can we do to basically eliminate that -2 I circled? We want to get that to be a 0. But we could take this bottom row and multiply it by 2, so that we have a 0, a 2, and a 4. And then we can add that to that first row, so that we end up with 1, 0, and 5. And then on the bottom, we still have 0, 1, and 2. We're not actually changing that second row right now, but we're using a multiple of it to add to the first row. But now we've got what we want. This is the matrix that tells us our answer. You could say, well, 1x plus 0y equals 5, 0x plus 1y equals 2. Or if you'd rather, you could say, well, the answer is x equals 5, y equals 2. So 5, 2 is the solution to this system. You could always plug that in, into the original equations. 4 times 5 is 20, minus 3 times 2 is 6, so 20 minus 6 is 14. X minus 2y equals 1. 5 minus 2 times 2, or 4. 5 minus 4 does equal 1. So that solution works in the system. Or those two lines, if you graphed them, would intersect at 5, 2. So I'm not entirely sure how they look, but they would intersect there at 5, 2. All right. So that is the Gauss-Jordan method. We apply the transformations, reduce the matrix down to diagonal form with 1s along the diagonal and then the 0s elsewhere. And then on the other side of that horizontal line segment there in the augmented matrix, we end up with our solutions. So this reduced row echelon form. So this form is called reduced row echelon form. So that's what that's called when you get it down to there. All right. How about we step it up a little? How about we do a 3 variable type situation? 3 equations with 3 unknowns. All right. Let's say we have x plus y minus 4z equals 10. 2x minus 3y plus z equals 7. 3x minus y minus z equals 12. I have to make sure I double check what I wrote down because it's so easy to make a mistake copying down the equations, and that throws everything off. In fact, when I was working out my notes to do this video, I made that mistake where I copied the wrong sign. And I was like, why is this not working? And then I went back, I was like, one of those dang signs. They'll get you every time. Okay, so let's write the augmented matrix first. So the augmented matrix, this one's going to have 3 rows and 4 columns. First row is coefficients from that first equation. 1, 1, negative 4. Little line segment there, 10. So those are the first row's elements. Second row elements will be 2, negative 3, 1, and 7. Third row elements will be 3, negative 1, 12. All right. We're going to follow kind of a L-shaped pattern, sort of. Almost like a Tetris looking pattern. We want the 1 up in the upper left corner first, and that's already there, thankfully. If it wasn't there, that would be our first goal, is to get a 1 there. Then we're going to work on the zeros here. And then we're going to make our way back this way here. We're getting our 1 and our zeros. And then finally worry about the rest of that top row. Getting our 0 and our 1, sorry. And then worry about the rest of that top row with the zeros. So we want ultimately to have that diagonal of 1s with the rest to be zeros. But we're going to work on it in this pattern because if you do it the exact way that the book says, often you're going to end up with nasty fractions. The pattern I'm going to show you will work, and you might be able to avoid nasty fractions. So that's why I'm going to show you this pattern rather than what the book likes to describe to do. So a little different method, like a little different order to approaching it, but I think you'll like it. All right, so we're going to leave 1, 1, negative 4, and 10 like where it is in row 1. That's not going to change. But I'm going to work on getting the zeros underneath the 1 first in that first column. So I'm going to take the first row and multiply by negative 2 and add that to the second row. So if I multiply that by negative 2, I'll have negative 2, 8, negative 20. If I go ahead and add that to the second row, I'll have 0, negative 5, 9, and negative 13. And if I use the same kind of thinking, and then take the first row and multiply by negative 3, I'd have negative 3, and 12. Add that to the third row. Negative 3 plus 3 is 0. Negative 3 plus negative 1 is negative 4. 12 plus negative 1 is 11. Then negative 3 plus... negative 3 times... Oh, I didn't write it down, sorry. Negative 3 times 10 is negative 30. I need that in there. So negative 30 plus 12 would be negative 18. So I got these zeros where I needed them. So I wanted to get the 1 in the upper corner, and I got the zeros underneath it. My next goal is going to be to get a 0 here at the negative 4. So I'm going to just get that little triangle of zeros. So how can I do that? Well, I don't want to add any, like I want to keep the 0 in the first spot there in that row. So I don't want it to do anything with the first row, because if I try to add, I'm going to end up changing that 0. I don't want to do that. So I'm going to focus on using the second and third rows, multiples of them, combining and replacing the third row with whatever that combination is. So it's again like using the elimination method. So let's say that I multiply the second row by 4 and third row by negative 5. Let's say I do something like that. Zeros won't change. 4 times 0, 0, negative 5 times 0, 0. But in that second row, I'd have, okay, negative 20, 36, and negative 52. And then the third row, I'll have 20, negative 55, and 90. I'm going to use those. The first row stays the same. Technically, second row is staying the same right now. It's just I'm using a multiple of it to add to that third row, a multiple of the third row. So if I add those multiples, well, 0 and 0 is still 0. Negative 20 and 20 is going to be 0. That's exactly what I wanted. I wanted these 3 to be zeros here. So look, notice like a little L shape. Then if I add 36 and negative 55, I end up with what? Negative 19. And if I add, let's see, so I ended up with negative 52 and 90. So that gives me what, 38? I say that with a questioning tone, like you can talk back to me right now. Anywho, I'm used to being in a classroom where I'm like, that's what I got. Do you verify? Yay. All right. Okay, anyways. So good. Good progress so far. That last row, that third row, negative 19z equals 38. We can already see that z is going to be negative 2. But humor me. Let's keep working. One of my next goals is to get this now to be a 1. And then I'm going to make my way back this direction. So for the next one, I'm going to divide by negative 19 so I can get my 1 there. But remember, you're technically dividing the entire row by negative 19, but the zeros aren't going to change, thank goodness. That makes things a little easier. So first and second rows for now are the same. Third row is now 0, 0, 1, and negative 2. Ooh, making really good progress now. Okay, now I'm going to make my way up, and I'm going to get this to be a 0. So I'm going to take the third row, multiply by negative 9, and add that to the second row. So 0, 0, negative 9, and 18. So technically the first and third rows are staying the same. So I'll go ahead and write those down so I don't accidentally do something to those. And then I'm using that multiple of the third row and adding it to the second row. So I'll still have 0 and 0. 0, negative 5 is 5. Negative 9 and 9 is 0. 18 and negative 13 is 5. Looking good. Now I want this to be a 1. So I can divide by negative 5 for that row. So I have a 1, a negative 4, and a 10. Last row is done. I can just rewrite it. That one will be 0, 1, 0, negative 1. That row is done. Looking good. All right, next slide. Let me rewrite that last one we just had so we have it to refer to. So we still have that first row to finish. All right, so we need that first row now. We need zeros here and here. So what can we do to accomplish that? Well, one thought is to take third row, multiply by 4. So you have 0, 0, 4, and negative 8. You can add that to the first row. So second and third rows are staying the same. Then first row plus the multiple of 4 times that third row. So 1 plus 0 is 1. 1 plus 0 is still 1. Negative 4 plus 0 is 0. 10 plus negative 8 is 2. All right, and then finally we need that 0 right here. So if we take the second row and just multiply by negative 1, so that we're using negative 1 here and positive 1 there. So second and third rows are staying the same. And let's see, 0 plus 1 is 1, negative 1 plus 1 is 0, 1 plus 0. Ooh, Okay, yeah. Sorry. 1 plus 0 is 1. I lost track of which row I was looking at. 1 and negative 1 is 0. 0 and 0 is 0. 2 and 1 is 3. And there we go. This last column here has our solutions. X equals 3, because 1x plus 0y plus 0z equals 3. Y equals negative 1, because 0x plus 1y plus 0z equals negative 1. And z equals negative 2. 0x plus 0y plus 1z equals -2. So our solution set is the order triple 3, comma, -1, comma, -2. And there you go. So that's how we do it, using the Gauss-Jordan method. All right, sometimes these systems don't turn out the way you thought they would. You've seen this in some of the other techniques where you might end up with no solution, or you might end up with infinite solutions. You can end up with some different things. So let's just take a quick peek at how that might look with matrices before we go on and look at one more method. Let's say you have 2x minus 3y equals 7. And let's say you have -6x plus 9y equals 0. And you want to use matrix methods to try to solve this system. And again, the name of the game is making this as simple as possible in ourselves, avoiding fractions and big numbers and that kind of thing if we can. So when I'm looking at this, even if I was doing this without matrices, one of my first things that kind of jumps out at me is that second row. I see that I could divide that second row through, if I wanted to, by like 3. I'm curious what that's going to get me. So the first row is going to stay the same. I end up with -2, 3, and 0. I'm very suspicious now because I'm noticing that first column has opposites, second column has opposites. Let's say I left the first row the same. Let's say I added the first row and second row together for the second row. Notice what happens. This is like having 0x plus 0y equals 7, or 0 equals 7. This cannot happen. It doesn't equal each other. That's false. So if you get a situation like that, where you get like all zeros on one side on one of the equations, and then still a number on the other side, and it's not equal to each other, then there's no solution to this. You might see the book use that symbol. What's the symbol? That's saying the solution set is empty. Or is the null set? The null set is empty. That's what that symbol means. It looks like a 0 with a slash through it. It's not a 0. It's a set notation, meaning it's an empty set. There's the solution. There is nothing in that solution set because nothing would work in this set. You can try all you want. If you were to graph these lines, you would quickly see that the two lines run parallel to each other. They never actually intersect each other, so that's why there's nothing in common between those two equations. All right, and then let's look at a situation where it's infinite solutions. That's the other kind of weird situation you might face. So let me find my example that I wanted to show you with that. 2x plus y plus z equals 5. 3x plus 2y minus z equals -8. Now don't look at this and automatically think, oh, that definitely is weird because there's 3 variables and 2 equations. That doesn't necessarily mean anything. I mean, you might be able to right now eliminate z and then try to solve, and you might get some kind of solution to this. But of course, I'm giving you a situation where that doesn't happen, so don't jump to conclusions prematurely. All right, it's going to be 2 rows by 4 columns. We're going to have 2, 1, 1, and then 5 to represent that first equation. And we're going to have 3, 2, -1, and -8 to represent that second equation. Now, by the way, if there's a variable missing, go ahead and put a 0 in there. So like if the first equation was 2x plus y equals 5, I would have put a 2, a 1, a 0, and then that 5. because, I want to make sure that everything lines up. So I need to make sure my x column is all values dealing with x's, my second column is all the values dealing with the y's, third column is all the values dealing with the z's, and the fourth column is all the values with those constants, what the equations equal. All right, so now let's apply what we know to trying to work on this. We want to get that 1 in the upper left corner, and then we want to get a 0 below it. And after that, we might start to seeing what's going on. So we want to start out with the same process that we were already doing earlier. There's a couple ways to do this. My first instinct is always, let me divide by 2 in that first row. But then you quickly get these nasty fractions. So it's nice to avoid that. So what did I do instead? Instead, I swapped the 2 rows. I decided to do this. If you can just add and subtract more often, you might be able to avoid some of those fractions. That's been a lifelong journey for me to learn to do that. I'm still stubborn, and often I'll try to jump and do it which way I immediately see to do it, and that's not always the easiest or efficient way, but whatever. All right, so let's take that first row, subtract with the second row, and then that's going to be the new first row. So 3 minus 2 gives me 1. 2 minus 1 gives me 1. Negative 1 minus 1 gives me negative 2. Negative 8 minus 5 gives me negative 13. Hey, looking good so far. Now, how about we multiply that first row by negative 2 and combine that with the second row. So keep the first row the same. Don't actually change it, but multiply by negative 2 and use those to add to the second row. So you get 0, negative 1, 5, and 31. That's what I'm getting. All right. Yep. And we're kind of stuck here. Because, you could go ahead and, multiply that second row through by negative 1 if you wanted to. And you would end up with 1, 1, negative 2, negative 13. 0, 1, negative 5, negative 31. So now you have the diagonal of 1s like you would like, and you have that 0 in place. But you really can't do anything further with this. This is an example of a situation with those infinite solutions. But you're going to be told to write the solution set with one of the variables arbitrary. So in this case, it's asking for z arbitrary. So what does that mean? All right, you've got x plus y minus 2z equals negative 13. And you've got y minus 5z equals negative 31. So what can you do with that? All right, we're going to keep z just as z. So our order, we're still going to have an order triple, but it's going to be written in terms of z. So how can we do that? Well, we can take the y minus 5z equals 31, and we can move z over. So that y is 5z minus 31. And we're going to write that in the spot for where the y would go in the order triple. So it's an expression for y in terms of z. And let's see, we could take the first equation, we could substitute that 5z minus 31 into it. I apologize, I'm going to have to come over here. I don't want to go to a new slide. So I'm going to take the x plus y minus 2z equals negative 13, and I'm going to replace y with that 5z minus 31. So I'm going to have x plus 3z equals, and I'm going to add the 31 over, so I get, 18? So x equals negative 3z plus 18. And that's going to go in the x spot here. So that's the order triple solution to this system. You're not going to find, there's actually multiple order triples that will work in these two equations. But they all have to fit this format. Like whatever your z is, you have to be able to do 5z minus 31 to get the y, And you have to be able to do negative 3z plus 18 to get the x. So you can have lots of ordered triples, but they all have to fit these formulas. Okay. All right, let's move on to one last thing, and then we'll basically be done with this introduction to matrices. We did the Gauss-Jordan method earlier, where we got the reduce the matrix to the diagonal form, where you had the diagonal of ones and then everything else was zeros. So we had that reduced row echelon form. And that final column gave us the solutions if we were solving equations. But we're going to kind of be a little lazier, and we're going to just get this down to row echelon form. Where we're just going to worry about getting the diagonal of ones with the zeros underneath those. And you can still have other, you don't have to worry about above the diagonal of ones. Then you can write your equations and then solve from there. So we're going to focus on just getting that triangle going here. The triangle of ones with the zeros underneath. So it's kind of a shorter one. So this is a Gaussian elimination. Instead of Gauss-Jordan, this is just Gaussian elimination. So same process. Actually, it's not really any different. We're going to be doing the same things we were working on earlier, where we're going to, get the one, get the zeros underneath, circle our way back around, get those ones. So it's not really going to feel any different. It's going to actually feel fast. It's probably going to feel faster. And that's a point the book makes. If you're just trying to figure out how many solutions there are, it's faster just to do this. Or if you have a very large system, it might be faster to get to here and then switch methods. So, there might be other reasons. But let's take a look at one more example. We're going to write our augmented matrix and then get that nice triangle with the ones and zeros and then work from there. Okay, so let's say we have x plus 2y plus z equals 5. 2x minus y plus z equals negative 5. Negative 3x plus y minus 2z equals 8. So our augmented matrix is going to have a 1, a 2, a 1, and then a 5. It's going to have a 2, a negative 1, a 1, and then a negative 5. It's going to have a negative 3, a 1, a negative 2, and an 8. All right, so I need to double check, make sure I copied it all correctly. Yay. So there's our augmented matrix. We've already got the 1 up here. Woohoo! So let's work on getting our zeros. What can we do? I'm going to multiply this first row by negative 2 and then add that to the second row. So I'm going to be using negative 2, negative 4, negative 2, and negative 10. Then adding that to the second row. So I got 0, negative 5, negative 1, negative 15. All right, then I'm going to use that first row again, and this time I'm going to multiply by 3 and add that to the third row. So I'm going to use 3, 6, 3, and 15. So I'm going to end up with, I'm going to keep, so first and second row staying the same. So I'm going to get 0, 7, 1, 23. All right, so far so good. Now I'm interested in getting the 0 here. So I think I'll do that next. Let's see. For now, let's keep this, we're going to keep the first and second row the same for now. going to change those just yet. But I am going to take, let's see how I could do this. I could take second row times 7 and third row times 5 and combine those. So I'll be taking -35, -7, -105, and then combining that with 35, 5, 115 down here. The zeros are stay 0. 0 plus 0 is 0. So I end up with my 0 there, my -2 there, 10 there. Okay, I'm getting this 1. It's really quick now, because then I can just divide by -2. So I get first and second row will be the same. I have 0, 0, 1, -5. So far, so good. My last point of concern is that right there. So what can I do with that? I mean, this method does want me to get a 1 there. I don't technically have to. I could go straight to just writing my equations and solving. I mean, if you really want to at this point, you could say x plus 2y plus z equals 5, -5y minus z equals -15, z equals -5. Oops, -5. But that's not the spirit of the lesson. The spirit of the lesson is to go ahead and get a 1 there. And honestly, I'm tired of trying to avoid fractions, so I'm just going to divide by -5 and not worry about it. So first and third row stayed the same. I just divided that second row by -5, and I got that 1 in there that I wanted. So by the third row, z is -5. By the second row, y plus 1/5 z equals 3. But I don't really want to use it that way. I mean, you can. All right, so if we plug in -5 in for z, we'll have what? Y minus 1 equals 3, so y equals 4. And then for into x plus 2y plus z equals 5, you can plug in, you're trying to solve for x, you know that x plus 8 minus 5 equals 5, because 2 times 4 is 8 there in the 2y. So x plus 3, so x equals 2. So your order triple is 2, 4, -5. So that's your solution to that system of equations. You can plug in 2 for x, 4 for y, and -5 for z into all 3 equations, and it will work. So those 3, in a 3-dimensional situation, those 3 planes would intersect at that one point out there in space. All right. So there's your introduction to matrices. We still got more where that came from. So stay tuned. Next lesson we're gonna dive further into matrices. But this is a good start. This gives you another technique for solving your equations. But there's more. So I look forward to joining you again in this matrix mayhem. And until then, have fun. See if you can avoid those fractions. If you can't avoid the fractions, you can still work it out. It just gets messy. So don't beat yourself up too much. Have your calculator handy, because it's nice to keep double checking all your calculations. It's so easy to make a little mistake and throw the whole thing off. This homework can end up being a long time just because of that. So I would say as you go, keep double checking your numbers. Try to do things so you avoid fractions, and go from there. All right. Thank you again.